Good afternoon. I'm Subashisa, Professor in Department of Civil Engineering, IIT Guwahati. This is the third time this river engineering MPTEL course is going on. So it's a quite interesting part to have a live interactions with you. So as we have a very few numbers that have joined this online live interactions. So my point today is to just highlight the basically as of now what we have completed so far. As of now, this almost 5 weeks have been completed. So first week we talk about sediment properties. Second week hydrodynamic principles. Third week also we extended the hydrodynamic principle to next level. Fourth is sediment transport, and fifth is physical modeling, which is introduction to the Scour, which is really a issues when you try to look for designing a bridge projects. Now let me look at that as a conceptually. If you look at the river, we divide it into three parts. The first part is offland areas where we have a source of erosions. Bed can go for degradations, and we can have a confluencing, channel confluencing, and the slope in definitely is steep, and bed material is more or less the gravel bed materials. This is its upper regions, which is source, the sediment source are the erosions. But the zone 2, where you have the river, have a transport process, and the mostly these traits of zone 2 river is at the equilibrium stage. Mostly it's a single channel with the meandering forms. Slope is mild, and it could have the gravel and the sand. That type of combinations could be there in zone 2 regions. And in zone 3 regions, you can see when you have a channel bifurcations will happen, the river deltatic formations will happen, where you will have a sedimentations will start it, the aggradations, the process will start it, river will be the branching it, and slope will be very, very gentle on the flat slopes. And in these part, you can see the sand and silt is the dominated part. So with this very basic concept, let me go to the next ones, how to find out the particle size distribution. I discuss in very detail in the class. So what we were trying to look at this percentage of fineness and the particle size. So these curve we can draw it using taking a samples from the maybe the riverbed samples or the bank samples. Then we can sieve the particles and we can get this particle size distribution. This plays a major role to talk about how the gradation curve is there. Is it a poorly or well-graded samples? This talks about how the river process are happening, or what is the strength of the bent materials or bed materials. So the particle size distributions is quite interesting to understand how it is happening. This is what is showing it, and it is giving examples of the different type of soils and what type of shapes is there. The well-graded shapes will be the S curve, and if you look at soil A, B, E, they are the dune sand will have this type of curves. Okay, so this is the particle size, and this is what the divisions from the clay, silt, sand, and gravels, and you can see that how different type of graded soil will be there. And here we are showing this mechanical sieve shakers, dry sieve analysis, and for the sand and the gravels, this is what we can do it. And now I think this part not to have this part. It is a summary that when we talk about the sediment particles, we talk about nominal diameters, we talk about area diameter, and we can talk about seep diameter, the fall diameter, and sedimentation diameter. And you know the sphericity is defined the ratio of the surface area of a sphere of the same volume that is given by sediment particle to actual surface area of the particles. So the result of the seep analysis present form of frequency of hydrogram, as I was showing you to you, a cumulative frequency curve. And we can have this non-uniformity of sediment mixes. We define in terms of D85, D50. So 84.1 indicates this is the diameters where the final particles will pass through it. Okay, what is the diameter of that? So 50 percentile and 15.5. So we can see that how we can grade or characterize the sediment particles. Now it's quite interesting things. If you look at the flow of a river system, so you can have the low velocity at the bottom. As you go off, you will have high velocity. Because of air tracks and all, your maximum velocity will be below the free surface. But if you look at the sediment concentrations, it will be high at the bed. As you go to the surface levels, your sediment concentrations can decrease. And that decrease can follow a exponential decay functions. So if you look at it this way, if I have the velocity, sediment concentrations, and the shear stress distributions follows like this. Okay, that these are the typical curve we can get it. How these sediment concentrations behave, the velocity profiles, and how the shear stress is varying. Now I'm not going very details about how we have derived these basic equations. This is one of the one-dimensional flow equations where we're deriving the mass conservation. But since it's a river flow, we also give an emphasis to the lateral inflow, because there could be a groundwater is coming into the river, or the river can also seep it, or water can seep from the river to the groundwaters. So that's the reason the lateral inflow has given emphasis to here. And the change of the storage, all the components are there, which follows a control volume concept to derive mass conservation equations or the continuity equations. So the basic idea is that we try to understand it. We follow very basic mass conservation equations and the linear momentum equations. This is what the one-dimensional unsteady open channel flow equations, where you can see that wind shear factors also consider it, and where you can have the energy slope, and those components we can always take it, and we try to look at how we can solve the problems, and which will be realistic to the conditions of the river in terms of stress development, in terms of linear momentum equations. This is what basically the velocity distributions of typical velocity distribution, and we should know it, how the secondary current formations are there, how to derive the flow durations curve or the sediment durations curve, and how the yearly variations of flow durations curve and sediment duration curve. That's what we'll talk about, how the flow is changing. This is the list of the equations, which is as you know it, these are Navier-Stokes equations, and in fluid mechanics in advanced levels, you can see these equations, which is here. Just I try to derive in the class or in the instructions levels, and if you can look at these equations are exactly fluid mechanics equation, but we can use it considering this, the three-dimensional component of this. Now I go for a very interesting part, which is we put in a bridge towers. So which is very interesting, and it is necessary, because if you look at these structures, all the sustainable, the stability of the structures are during the high flood period. It depends upon how much deeper scour hole formations are happening. And it is what type of vortex formations are happening here. And this is what is, today we have a series of numerical model. Also, we can see that how velocity distribution, the shear stress, how the bed particle movement also we can look at. So we have it. Here we talk about how you design, how do you prepare the design guidelines. That is, we first identify the hydraulic problems, like the scour estimations, or derive the design guidelines for scour protection or the scour hole depth estimations. So first, what we look at physical models and river models, do a dimensional analysis, then develop a empirical relationship, and you also do it the river level field measurement experience. And based on this, all this knowledge, we prepare design guidelines. So because it's a very interesting problems, because there is a flow, there is a sediment, okay, bed materials there is a flow is coming in and going out, there is a hydrodynamic, the velocity field, the pressure field, all are changing it. Also these structure interactions are happening. Considering all these effects, we try to look at a design guidelines. We try to look at design guidelines. How we do it? We take physical river models, like you can see these figures, okay, physical river models. Okay. You can have a river mathematical models also giving approximate solutions for us. Do a dimensional analysis, develop a series of empirical relationship with scour depth, with stream power, the velocity, the depth, the structure informations in terms of bridge spire dimensions, all we can include it, and finally we establish a relationship which we can also test at the field level. That means at the river level, we can put the instrumentations and estimate how. And after having a thorough analysis of these knowledge systems, what we gather from physical river model, mathematical model, dimension analysis, and the field measurement, that's what we prepare a design guidelines. So most of the time we follow this procedure to prepare a design guidelines for bridge spire designs, abutment design, river protections work. So that Indian Standard Code of Design Guidelines will prepare it, conducting a thorough analysis at the physical level, model levels, field measurement, and the dimensional analysis. So I'm not going detail what type of scour it happens, general scour, contraction scour, the local scours, as you know it. Just I am to highlight it that how just have to constrain the channels. If the channel is coming a width of B1, but you reduce a depth width of the B2. Generally, whenever you have a river, a bridge construction, so we constrain the channel. We reduce the width of the channels. So once you reduce channel from B1 to B2, you see these flow patterns, how it's happening. There is a local abutment scour. This maximum scour will happen at these points. Okay. There will be a backwater scouring as contraction scours. All this process will happen if we constrain the channel. And here it is showing it how it is happening. So I do believe it. I try my level best with this 8 weeks instructions. I try to cover the river engineering. Considering both mathematical modeling part, the empirical things, understanding from the field, understanding from the laboratory, because as you know it, river engineering is a very complex, and as we know it from second law of geography, the river A or river B, they may look similar, but their process are different. Their response to a change always will be the different. So that's the reasons each river we should understand with our knowledge, or we can try to explore to know more about that rivers, conducting a series of experiments, maybe the mathematical model level or the physical model level, then try to get the solution for that. So as you know it, the river, as we have been anthropogenically disturbing the catchment area, It is changing the river courses, it's changing the river bed materials. We have been constructing a lot of bridges. We have been confining the rivers. But as a river engineering, we should have a knowledge that how this river going to respond to that when you are doing that anthropogenic changes. So that is idea to present this river engineering, because if you do extremely anthropogenic disturbance to a river systems, which will change one form to others, we cannot reverse back it. So looking at extreme conditions and looking to understand the river, or each river have a unique hydrodynamic sediment and the interactions with the structures, we should try to understand how it is changing. So with this note, I do believe it. We try to do as much to compiling the knowledge from internationals and the Indian standard codes to prepare this river courses in SWAMPL platforms. So now, if you have any query, and you can chat with me. Any query? As I know it's there are. Please chat with me, or they can put the questions to me directly. They can ask the question directly to me.
Yes.
Yeah. Please, if you have any questions, doubt, or suggestions, please interact with me. It's quite interesting in this course, in these semesters, we have more than 1,000 students. They have already registered this course. Okay. It's quite interesting and encouraging to us. Please post the queries. You can ask the questions too. Yes, there is no query and questions. So we'll wait for maybe another 2 to 3 minutes. Any questions and query, please drop it. So because we can, if there is no questions and queries, so we'll be closing this sessions, live session. And to tell you, what is the questions? To tell you, blessed. Shashi Shankar, sir, I'm totally. Sir, no questions. Okay, no problems. No problem. Any questions, people? Any questions who are interacting with? I know it's online are nowadays, the live sessions are not much. Please post any query or any suggestions, any sustainable energy technology assignment, how to get high mark. Okay, the Madan Gokul. So okay, what I'm getting it, how to get a high marks. Madan Gokul, actually we have been trying our level best to put very easy questions. Okay. But looking the standard of this river engineering course, okay, but initial assignments are the top, because initial assignments are from the Sediment equations, from the equations of Navier equations and all. But later on, so you will have a very easy concept will come it. One is that river bank protections and all, which are quite empirical natures. So what I do encourage you to, don't worry about initial marks, what you are getting it, because the initial part of the course is a bit tough, because we cover a mathematical part so that you can understand this mathematics more about the river engineering. But when you come to a design part, I think that's not a big issue for you, because that will be very, you can easily score high marks in design part, which is there later on, maybe after 5th and 6th and 7th week. You can easily score high marks. There are no problems at all. Any questions for that? Is it okay, Mr. Madan Gokul? Yes, anybody? Okay, thank you. It's okay. So the basically, I think there is no more questions. So with this, we can. Okay. So just we're waiting for another 2 minutes. If you have anybody have any questions to us. Before that, I have to tell it that this river engineering course is one of the fundamental course we have developed it, looking our river conditions now. Either you have a over-exploited river with a series of hydrodam projects, or we are at too much fear to implement the hydropower projects, or so we have to sustain the river. So that is the reason this course very strategically designed such a way that students should understand at the international level what the river engineering is going on, and what is the Indian practice for the river bank protections or any scour designs and all. So we try to put it a level playing field for looking the international aspect as well as the local aspects. Any questions further? If not, thank you all for attending these live sessions with me. Okay, and so this is the 3rd year we are conducting this river engineering courses. So, and having more than 100 registered participants in this course is quite encouraging, and really I enjoy even in these live sessions. Thank you all.